Hello everyone, my name is Ignacio Mateos and I'm gonna talk about a CubeSat mission developed at the University of Cádiz in Spain with the support of the European Space Agency. The title of the talk is UCAnFly, a CubeSat to test magnetic sensing technologies for gravitational wave detectors in space. To begin with, this is the well-known formula within the LISA consortium, with the top-level requirement of LISA in terms of the single test mass acceleration noise spectral density. This total noise is the result of various disturbances of instrumental and environmental origin. At low frequencies, the noise is dominated by the drag-free control and environmental contributions such as magnetic and thermal effects, charge fluctuations, Brownian noise from molecular impacts, etc. Focusing on the magnetic effects, the equation below shows how the magnetic properties of the test mass, more precisely the resonant magnetic moment and the magnetic susceptibility, chi, coupled with the surrounding magnetic field and magnetic field gradient, provoking a non-gravitational force on the test mass volume. So for this reason, magnetometers need to be integrated in the spacecraft to produce a map of the magnetic field and gradient in the region of the test mass, and then to quantify the magnetic contribution to the total acceleration budget. The problem of magnetic sensing in LISA has naturally been addressed first in LISA Pathfinder, also with the purpose of monitoring the high-frequency magnetic disturbances caused by the satellite and the time-varying interplanetary magnetic field critical at the lower end of the bandwidth. So the magnetic diagnostics for LISA will be based on the previous experience with LISA Pathfinder, which consists of two main parts: the main measurement subsystem with 4 flat-gate magnetometers around the LTP, and a dedicated unit that injects controlled magnetic field with high signal-to-noise ratio by means of 2 onboard coils attached to the external wall of the vacuum enclosure. The flat-gate magnetometers for LISA Pathfinder were chosen because of their excellent sensitivity and availability for space applications. However, some drawbacks were identified which point to the need of a different technology more suitable for LISA. First, flat-gate sensors need to be placed far from the test mass due to the quantity of ferromagnetic material contained in the sensors in the core of the sensor that can provoke magnetic disturbances on the test mass. Floodgates are also heavy and bulky, and this reduces the number of magnetometers that can be incorporated in the satellite, thereby also reducing the accuracy of the magnetic field map in interpolation. And sensors and electronics need to be assessed in the LISA bandwidth. The noise of the subsystem is good enough at LISA Pathfinder frequencies, but out of the requirements at the lower end of the LISA bandwidth, mainly due to the signal conditioning circuits. So in order to overcome the above limitations, we are currently investigating alternative magnetic sensing techniques for space missions with strict constraints regarding magnetic cleanness and long-term stability. We have several ongoing projects at the University of Cádiz for developing atomic magnetometers in collaboration with Berkeley, with UC Berkeley, and with the Helmholtz Institute. Additionally, we are working on another project for different types of magnetoresistive sensors, such as TMR, AMR, and GMR. So here you can see some highlights for AMR sensor. They are chip scale sensors. In the left figure, we show one AMR sensor viewed with an electronic microscope, and in the right figure, the size comparison with the conventional flat gaze used in LISA, in space application, in this case in LISA Pathfinder. AMR sensors have lower power consumption than flat gaze, and because of these 2 points, a more numerous array of sensors can be integrated in the spacecraft, increasing the accuracy of the magnetic field map estimation around the test mass. However, solid-state magnetometers, they exhibit a dominant 1/f noise power spectrum over the LISA requirement at 0.1 MHz. Therefore, we have studied and compared the noise performance of the sensor at sub-millihertz frequencies and their effects, their behavior for different electronic noise reduction techniques. In this reference, we show how these techniques help to enhance the performance of the sensor necessary to achieve the requirement for LISA. Also, the complete subsystem has a TRL4. So, with the objective of increasing the technological maturity of the instrument, the magnetic measurement subsystem design has been developed for a CubeSat. And this is UCAnFly, an educational CubeSat mission led by the University of Cádiz that was selected by the European Space Agency in 2020 within the Fly Your Satellite program of the ESA Educational Office. The UCAnFly team is formed by a multidisciplinary group of young researchers, students, and collaborators in charge of designing and building the satellite at the university. The team benefits from direct knowledge transfer of ESA, as well as access to facilities for the environmental tests in phase D2, and a launch opportunity, of course, if we successfully pass all the mission phases. In the UCAnFly mission, we propose a magnetic measurement subsystem called MELISA, based on chip-scale magnetoresistive sensors to be integrated on a one-unit CubeSat, which will make it possible to elevate the technological maturity of the instrument from the current TRL4 to 6. Here we have the electrical power subsystem, 2 redundant payloads, and the OBC based on dual CPUs in lockstep mode to correct single event offset. In the same board of the OBC is also included the ADCS sensor and the communication subsystem. The special feature of the experiment is that the magnetic sensors integrated into the payload are magnetically shielded to low frequency fluctuations by using a small cylindrical permalloy enclosure. This will allow the in-flight noise characterization of the system and will make it possible to analyze the relationship between the in-orbit radiation environment and the possible low-frequency noise degradation of the magnetic sensors at LISA frequencies during a 1-year mission. UCAnFly is currently in phase C with the CDR at the end of the year, and the expected launch date is 2022. Magnetic and thermal fluctuations are critical at low Earth orbit for sub-millihertz measurements. For this reason, the payload has been designed with passive and active techniques to mitigate the effects. In order to assess the ability of the in-flight characterization, environmental fluctuations in the lab were compared to LEO environmental data obtained with the ESA SWAM satellites at 2 different altitudes. And as shown in the left figure, the magnetic noise at lower frequencies for the LEO data exhibits a contribution that exceeds the environmental noise in the lab. These noise contributions are linked to the Earth's magnetic field variation along the spacecraft orbit. Okay, and as I said before, the AMR magnetometers were placed inside a 3-layer cylindrical enclosure of mu metal to shield the environmental magnetic field down to the nanotesla range. The magnetic environment and the behavior of the shielding are being simulated with finite element method by using ANSYS to estimate the attenuation factor obtained for the different layers of the mu metal enclosure. The estimated maximum attenuation factor of 60 dB will not be enough to cancel out the magnetic contribution. Therefore, post-processing analysis will be done during in-flight operations of the CubeSat to correlate the magnetic data with another non-shielded magnetometer in the CubeSat and then disentangle the possible magnetic effects. Okay, in the right figure we see a prototype of the payload with the magnetic shielding already integrated. From the thermal point of view, the wide variation of temperature during a 90-minute orbit poses a major threat to the precise measurements required for the payload due to the thermal dependence of the electronic components. To reduce the excess noise at low frequencies caused by the thermal drift, we implemented different active techniques such as modulation and compensation techniques. So, as shown in the block diagram, the sensing element is composed of a Wheatstone bridge of AMR. The signal is modulated, amplified, synchronously demodulated using a phase-sensitive detector, integrated and digitally converted by an ADC. Then, to maintain high accuracy over temperature, the drift of sensor sensitivity is compensated during operation. So, a closed-loop circuit is included in which a current regulator fits the compensation coil, maintaining the output of the sensor less sensitive to temperature. The skin of the analog conditioning circuit, considering the most relevant noise sources and the closed loop response of the system, are shown below in the left, and the noise estimate of each stage was quantified analytically and verified by on-ground measurements. Among the different noise contributions of the circuit, the one from the instrumentation amplifier and the ADC become relevant at frequencies about 10 Hz, but the critical source in the bandwidth of interest is the 1/f noise, the intrinsic 1/f noise of the sensor. The modulation and the closed loop techniques are performed to ameliorate the noise curve of the system along the LISA bandwidth. Okay, this spectrum shows the noise data of the 3 sensor axes taken with the small mu metal magnetic shield already integrated in the payload. The dashed blue line shows the equivalent magnetic field spectral density of the payload down to 0.1 millihertz. And as can be seen in the figure, the equivalent magnetic field noise is within the requirement with the proposed dedicated design. Finally, I summarize in this table the main performance of the payload, such as temperature coefficient, sensitivity, spatial resolution, which is lower than 1 millimeter, power consumption in the different modes, etc. I don't have time to go through it in detail, but here it is in case you want more information. And that will be all from my side. Thank you for listening, and if you have any questions, please don't hesitate to to contact me through the LISA Symposium platform or by email. Thank you again. Bye bye.